Ever wondered how devices on a network automatically get their IP addresses? Well, that magic is largely thanks to something called DHCP, or Dynamic Host Configuration Protocol. This nifty protocol is essential in the world of network management, playing a pivotal role in how devices on a network communicate. DHCP stands for Dynamic Host Configuration Protocol. It's like the efficient admin of a bustling digital city, dynamically assigning IP addresses to devices as they connect to the network. This process isn't just about giving out IP addresses randomly. It ensures that each device gets a unique identifier that helps in smooth network communication without any IP conflicts. The brilliance of DHCP lies in its ability to manage these addresses dynamically. It's crucial for modern networks where devices frequently join and leave. By automating what was once a manual setup, DHCP saves network administrators considerable time and effort, making it easier to scale networks and adapt to changes. Now let's dive deeper into how DHCP actually works. Imagine you just connected your device to a new network. What happens next is a fascinating dance of digital communication, primarily choreographed by DHCP, or Dynamic Host Configuration Protocol. Let's delve into the magic behind this process. When a device links up to a network, it's essentially an unknown entity to that network. To carve out its own space, the device sends out a DHCP discovery broadcast. This is essentially a digital shout into the network, saying, "Hey, I'm here and I need an IP address." This broadcast is crucial because without an IP address, the device can't communicate effectively within the network. The DHCP server, which you can think of as a kind of digital traffic controller, picks up on this broadcast. It's always listening for such calls from devices seeking to join the network. The server has a pool of IP addresses at its disposal, which are set aside specifically for dynamic assignment. Upon receiving the discovery request, the DHCP server selects an available IP address from this pool. But it doesn't just send this IP address back willy-nilly. Instead, it sends a DHCP offer message to the device. This isn't just any message, it's packed with essential network configuration parameters. Along with the IP address, it includes the subnet mask, which defines the network segment the device is on, the default gateway, which the device will use to send data to devices on other networks, and DNS server addresses, crucial for the device to convert human-friendly domain names into IP addresses it can understand. Why all this effort? Well, by automating this process, DHCP servers eliminate the need for network administrators to manually assign IP addresses to each new device. This not only saves time but also significantly reduces the potential for errors, such as IP conflicts where two devices end up with the same IP address. With the network alerted to its presence, the device now awaits a response. The network responds to the call. When a device first connects to a network, it sends out a digital flare, a DHCP discovery message, signaling its need for an IP address. This message reaches the DHCP server, a diligent entity ready to manage the network's IP resources. The server, upon receiving this request, doesn't just send back any response. It crafts a DHCP offer message, a packet filled with not only an IP address but a suite of other crucial network settings. This includes the subnet mask, which defines the network segment the device will belong to, the default gateway, the primary route through which the device will send data to other networks, and DNS server addresses, which are essential for the device to translate domain names into IP addresses. This offer is not a binding agreement, but rather a proposal, pending the client's acceptance. The IP address provided is chosen from a pool of addresses that the server manages, specifically set aside for dynamic assignment. This ensures that each device on the network can have a unique identifier without conflict. Moreover, the offer includes the lease duration, which dictates how long the device can use the IP address before renewing it. This aspect is critical for maintaining an efficient and flexible network, allowing addresses to be recycled and reassigned as devices come and go. Once the offer is out, the ball is in the client's court. The client decides it's a deal. Following the receipt of the DHCP offer, the device now sends a DHCP request message back to the server. This is the client's way of saying, "Yes, I'll take the IP address you've proposed." The request message is a crucial step, confirming the acceptance of the IP configuration previously offered by the server. Upon receiving the request message, the DHCP server springs into action. It needs to ensure that the IP address it offered is still available and hasn't been assigned to another client in the interim. Assuming all checks out, the server proceeds to the next crucial phase, acknowledgement. The DHCP server now sends a DHCP acknowledgement message to the client. This isn't just any message, it's packed with important details. It confirms the IP address assignment and includes essential network configuration parameters, such as the subnet mask, default gateway, DNS server addresses, and the duration of the lease. This acknowledgement message is essentially the green light telling the client that it's good to go, that the network parameters are set, and the IP address is officially theirs for the duration of the lease. This exchange is not merely about assigning an IP address, it's about integrating the device seamlessly into the network. It ensures the device can communicate efficiently with other network entities and reach the broader internet. And just like that, the device is part of the network with its own unique IP address. But how does the DHCP server manage possibly thousands of these addresses? Imagine a bustling city where every inhabitant needs a place to live. In this city, the DHCP server acts as a sort of digital real estate agent, dynamically allocating spaces, or in our case IP addresses, from a pool specifically configured for this purpose. This pool isn't infinite. It contains a finite number of addresses that the DHCP server must manage judiciously to ensure that each device connecting to the network has a unique home or IP address. So, how does the DHCP server keep track of which addresses are occupied and which are available? It meticulously records each IP address it assigns, along with the lease duration. That's the length of time an IP address is assigned to a device before it needs to be renewed. Another fascinating aspect of DHCP management is the concept of DHCP reservations. This is particularly useful for devices that need to retain the same IP address every time they connect to the network, such as servers or printers. Effective management of IP addresses by the DHCP server not only maximizes the utilization of the address pool, but also ensures that each device on the network can communicate efficiently without the risk of IP conflicts. It's a continuous process of monitoring, updating, and reallocating that keeps the network fluid and functional. Effective management ensures every device connects smoothly without IP conflicts. Nothing lasts forever, not even IP leases. In the world of DHCP, the concept of a lease duration is crucial. This is the set period during which a network device is allowed to use an IP address. Typically, this could range from a few hours to several days, depending on the network's policy and the device's needs. As the lease nears its expiration, the client device must actively renew its lease to continue using the IP address. It does this by sending a renewal request to the DHCP server halfway through the lease duration. This proactive approach helps avoid connectivity issues. Should the client fail to renew its lease, perhaps due to being turned off or disconnected, the DHCP server reclaims the IP address. It then returns this IP address to the pool, making it available for assignment to other devices. This recycling of IP addresses ensures that the network can support new or returning devices without running out of resources. This dynamic renewal process helps maintain efficient network operation. So we've seen how DHCP plays a vital role in network management. Let's take a moment to recap the journey of a DHCP server and its critical functions in the digital network landscape. Initially, we explored how DHCP servers dynamically assign IP addresses. When a device joins a network, it triggers a DHCP discovery, leading to an IP address offer from the server. This process ensures that each device is uniquely identified on the network without any manual setup. We then delved into how these servers manage and monitor IP addresses to prevent conflicts and ensure optimal network performance. The ability to reserve specific IP addresses and manage a pool of addresses highlights the DHCP server's role in efficient network administration. Furthermore, we discussed the automatic renewal and lease management features that maintain seamless network connectivity. DHCP servers automatically handle lease renewals, which keeps network connections stable and reliable. Lastly, the importance of fault tolerance and redundancy in DHCP servers ensures that even in the event of a server failure, network functionality is preserved, preventing downtime and data loss. Thanks to DHCP, network administrators have one less headache to worry about. Remember, a well-configured DHCP server keeps the digital world spinning smoothly.